Hey everyone, and welcome. Today, we are going to dive into a really core concept in machine learning called multiclass classification. And we're going to do it by starting with a simple question about penguins, and by the end, you'll see exactly how we can build and judge a really powerful predictive model. So let's get right into it.
So it all kicks off with a pretty simple problem, right? You see a penguin, and you've got to figure out what species it is. Is it an Adelie, a Gentoo, or maybe a chinstrap? Now, the key thing here is that this isn't a simple yes or no question. There are multiple possible answers, and that is exactly the kind of challenge we're talking about today.
So here's our game plan. First, we'll cover the what this whole thing is. Then, we'll use our penguin example to make it all feel real. After that, we're going to peek under the hood a little and see how a model actually learns, watch it make some predictions, and then finally, figure out how we grade its homework.
Okay, so let's jump right in. What are we actually talking about when we use this term multiclass classification?
Well, at its heart, it's basically a sorting problem. You might have heard of binary classification. That's kind of like a light switch. It's either on or off, yes or no. But multiclass, that's more like sorting mail into a bunch of different mail slots. The whole goal is to look at one piece of information and assign it to one of several distinct buckets or categories.
And this isn't a one and done kind of thing, it's really a cycle. First, you have to train the model. You do that by showing it a ton of examples where you already know the right answer. It's kind of like a student studying with an answer key. Then you validate it by giving it a pop quiz with new problems it hasn't seen before. And finally, you evaluate the results of that final exam to see if the model is actually ready for the real world.
Okay, enough with all the abstract theory. Let's make this whole thing super concrete by meeting our feathered friends.
So here is our mission, plain and simple. We want to teach a computer to figure out a penguin species just by looking at one single clue, the length of its flippers. Now, obviously, in the real world, you'd probably give it a lot more clues, but for now, we're keeping it simple just so the concept really stands out.
This right here, this is the kind of data our model gets to learn from. On the left, you've got the flipper length, and on the right, you see the species. But notice how we've turned the names into numbers. 0 for Adelie, 1 for Gentoo, and 2 for chinstrap. The model's whole job is to figure out the secret pattern that connects these two columns.
So, the big question is, how does the machine actually learn from data like this? I mean, it's not magic, right? It turns out it generally uses one of two main strategies, and each one has a totally different way of thinking about the problem. And what's awesome about this is how you can simplify these two pretty complex ideas. Think of one versus rest as playing a game of 20 questions. It just asks a series of yes or no questions. But the multinomial method, that's more like a multiple choice test. It looks at all the options at once and just picks the one that's most likely. Now, you might go with one versus rest because it's simpler, but multinomial can often be more powerful if you've got the computing power for it.
Okay, let's zoom in on this one versus rest idea. This strategy is kind of like training three completely different specialists. The first specialist only knows one thing, how to spot an Adelie. The second one, only a Gentoo, and so on. So when a new unknown penguin shows up, we basically ask all three of our specialists for their opinion, and whichever one shouts the loudest, has the most confidence, that's the one who gets to make the final call.
Now, the multinomial approach is more of a generalist. It builds just one single smarter model that weighs all the possibilities at the same time. So for any given flipper length, it spits out a confidence score for each species, like you see here. It might say, I'm 20% sure it's an Adelie, 30% sure it's a Gentoo, but I'm 50% confident it's a chinstrap. So guess what? It picks chinstrap.
All right, our model's been trained. Now comes the moment of truth. Let's give it some new data. Penguins it has never ever seen before, and let's see how it does. And here are the results. The middle column, that's the real answer, and the column on the right, that's our model's best guess. And you can see, it did a pretty great job, but it wasn't perfect. It stumbled on one of them. Take a look at that row in bold. The model saw a chinstrap penguin, but it confidently and incorrectly called it a Gentoo. But just saying it got one wrong isn't a very scientific way of looking at it, is it? We need a formal, standard way to measure the performance. So, how good is our penguin sorter really? And this thing right here brilliantly shows us exactly where the model got things right and where it got confused. It's called, fittingly, a confusion matrix. See the numbers on the diagonal, from the top left to the bottom right? Those are all the correct answers. Any number off that diagonal is a mistake. And there it is. You can see our one error. The model predicted Gentoo for one penguin that was actually a chinstrap. Now, this matrix is fantastic, but we can actually distill it down even further into a few key numbers that give us a nice, high-level summary of how the model did. First up is the most famous one of all, accuracy. It's the one we all kind of get intuitively. It just answers a simple question: what percentage of the time was the model right? In this case, it got 9 out of 10 penguins correct, so that gives it a solid 90% accuracy score.
Next, we have something called recall. Now, this one gets a little more specific. It asks, of all the penguins that were actually chin straps in our test group, how many of them did our model successfully find? See, a high recall means our model is great at not letting anything slip through the cracks. It's really a measure of completeness. And finally, we've got precision. This kind of flips the question around. It asks, of all the times our model claimed a penguin was a Gentoo, how often was it actually right? A high precision means that when our model makes a call, you can be really confident that that specific prediction is correct. It's a measure of exactness.
So why do we have all these different numbers? Well, because accuracy by itself can sometimes be a little misleading. Recall and precision are like diagnostic tools. They help us understand the type of mistakes our model is making. Is it just missing things it should have found? That would be low recall. Or is it making confident but wrong guesses? That's low precision. These are absolutely essential tools for any data scientist.
And this brings us to the last and maybe the most important question. These numbers, they're objective. But whether a score is good, well, that's completely subjective. For just sorting penguins, hey, 86% might be amazing. But what if this model was being used to diagnose a serious disease? Suddenly, that same score doesn't look so good. The context of the problem is everything. And that's something to think about every single time you see a model score.